Students, we will take a problem related to the laced columns. Design a laced column 9 meter long to carry a factored axial load of 1200 kilonewton. The column is fixed at both the ends, provide single laced system with a bolted connection. The column consists of two channels placed back to back. So the given data, length of column 9 meter, end condition fixed at both ends, k equal to 0.65, which is taken from table number 11 for the given end condition. The axial load is given 1200, it is a factored axial load. Now let us initially assume the approximate design compressive stress equal to 125 Newton per millimeter square. First step is to design the column as usual. The area of the column required equal to 1200 divided by design compressive strength. So for calculating the area, we need this compressive stress. It works out to be 9600 millimeters square. The column consists of two channel sections which are placed back to back, which is given in the problem. Therefore, one section will have a area of 4800 millimeters square. Now from the steel table, let us select ISMC 350 at 413 Newton per meter. The properties of this steel section is noted down. The area is 5366 millimeter square, which is greater than 4800 millimeter square. So it is okay. You note down all the remaining properties. This is how we are going to place the channel. And let us assume the channels are placed at a distance of S like this. Back to back placing with a distance of S. So with respect to this axis, or this line, middle line, this distance is S by 2, this is S by 2. This is CYY. This may be required for later few calculations. Second step to check the suitability and safety of the section chosen. We have to check whether the given section is okay for us or not. The slenderness ratio lambda equal to KL divided by RZZ 0. I have to get the maximum slenderness ratio. Therefore, RZZ I have to consider 0.65 into 9000 by 136.6, 42.825. As per clause 7.6 IS 800-2007, this value should be increased by 1.05 times. So upon increasing, we get the slenderness ratio as 45. Now from table number 9C, you calculate what is the FCD value. The design FCD value works out to be 190.5. This 190.5 is greater than the initially assumed value 125. So it is okay in this step itself. Further, we will calculate the design compressive load PD equal to AE into FCD. 2 into 5366 because we have two channel sections into 190.5, 2044.46 kilonewton greater than 1200 kilonewton. It is safe. Now we have to calculate the distance or spacing between these two. That is yes. For that, let us have the basic formula 2IZZ equal to 2IY plus A into S by 2 plus CYY whole square. Upon substitution of the values, S is the unknown, we can calculate the value of S. S works out to be 218.39 mm. However, we will provide the distance between two channels as 220 mm. In the third step, we have to do the design of lacing. The design of lacing is very important. So let us provide the lacing bar at 45 degree to the horizontal. In the clause it is given, you can take from 40 to 70 degree. Usual practice to take the 45 degree. Let us assume a gauge length of 50 mm. The horizontal distance between the bolt line equal to now, this is a bolt line here, these dotted lines are bolt lines, this one and this one. The distance is 220 plus 50 plus 50, it is 320 mm. Now the spacing between lacing bars L0 equal to 320 into tan 45 into 2, it is 640 mm. So this distance we want, this distance it can be easily calculated. 320 into tan 45, this is 1 and this is second, so into 2, so it is 640 mm. Therefore, L0 divided by RYY should be less than 0.7 times L by R of whole column. So we will have that check. According to that check, we get an answer 22.61, which is less than 29.97. It is okay. You can show the detail of lacing. Now from clause 7.6 IS 800-2007, the transverse shear should be equal to 2.5 times the axial load. It is 30 kilonewton. Now the transverse shear in each panel is half of that, which is equal to 15 kilonewton. Therefore, the compressive force in the lacing bar is equal to 15 into 10 raised to 3 divided by cos 45, because here I have the shear. This is a shear. This is a compressive force. This is 45 degree. So I want this. This is nothing but the, yeah, this is nothing but the 15, and I want this force. So it works out to be 21.21 into 10 raised to 3 Newton, or 21.21 kilonewton. This is the design force for the lacing. Now we assume 16 mm diameter bolt from clause 7.6.2 IS 800-2007, we can fix the dimensions of the lacing. The minimum width of the lacing flat is 48 mm, 3 times the diameter of the bolt, and minimum thickness should be 1 by 40 into effective length of single lacing. So 1 by 40 into 320 divided by cos 45, the effective length I want to calculate. It works out to be 12 mm. Therefore, provide lacing bar of 50 by 12 mm size. A flat bar I have to provide. You calculate R minimum. R minimum is nothing but thickness divided by square root of the thickness, which is 3.464 millimeter. Therefore, you calculate the slenderness ratio of lacing bar LE divided by R, that is 320 by cos 45 divided by 3.464. Answer is 130.64, which is less than 145. It is safe. Now, for buckling, for flat bars for buckling class C, lambda equal to 130.64, or KL by R is 130.64, and Fy equal to 250 Newton per millimeter square. Buckling class C, you calculate FCD. FCD is 75 Newton per millimeter square, and design compressive strength PD equal to 45 kilonewton, greater than 21.21 kilonewton. It is safe. Now check the tension in the lacing bar. We have to do the two checks. One is design strength against rupture, works out to be 113.36 kilonewton, and second one is design tensile strength against yielding, TDG, works out to be 136.36 kilonewton. Out of these two, least value should be greater than the compressive force. It is okay. Next is design of connection. We know a bolted connection is adopted. So design strength of bolt in shear is to be calculated. We have already studied this procedure. So in this case, one bolt will tie two lacing plates at a particular joint. So the bolts will be under double shear. So 2 into FUB by root 3 into gamma MB into A and B. So I get 57.97 as the answer. A and B is 0.78 times pi by 4 into 16 square. Finally, you calculate design strength of bolt in bearing also. So this procedure, when you know, I will not explain much about this. You assume the edge distance and pitch distance according to the code provisions, and we get a bolt value equal to 57.94 kilonewton, and you calculate the number of bolts required. The load divided by bolt value 21.21 by 57.94. The answer is 0.36, rounded off to 1. And finally, you have to do the design of tie plates. So usually these tie plates are provided at the top and bottom of the compression member only. So the effective depth of the tie plate should not be less than the distance between centroid of main member. So that is equal to S plus 2 into CYY. The answer is 268.8 mm. Assuming 30 mm edge distance or clearance at the end, the total depth of the tie plate is 268.8 plus 2 into 30. The answer is 328, rounded off to 350. Now, the width of the tie plate is equal to the total outer to outer width of the column itself, 220 plus 2 into 100, 420. The required thickness of the plate is 1/50th of 1 by 50th of width or effective length. The answer is 8 mm. Therefore, we provide a tie plate of 420 by 350 by 8 mm at both the ends with the 6 number of bolts of 16 mm diameter. This is how the plan looks like. Here we have two channel section. These are two bolts, and these are the bolts, and these are the lacings. So this is how we can look in the case of elevation. Here you can see the tie plate, and this is nothing but the lacings. So the tie plates, totally we have 6 bolts provided, 6 of 16 mm. Here I have a 1 bolt and here also at the end I have another bolt for lacing. This is how you can do the design of laced columns. Thanks for watching. Any doubts you can ask it anytime. Thanks once again.